Okay, welcome to lecture number 11 of the course on fundamentals of transport processes 2. In the last lecture, we were just deriving the mass momentum conservation equations. We had defined the stress and we were just going through the angular momentum conservation equation. So, let us just briefly review what we did in the last lecture. Mass conservation. Start off with a differential volume in this coordinate system. Okay. This differential volume dV with a surface S. Differential volume is a material volume. That is, I have a fluid which is moving and there is a fluid velocity which is specified at each point within the fluid. So, I have a fluid velocity field. And this volume is defined to be a material volume, that is, all points on the surface move with the same velocity as the fluid velocity at that point. So, if I have some fluid velocity field, all points on the surface move with the same velocity as the fluid velocity at that particular point on the surface. Okay. Consequence of that is that points that are inside this volume continue to remain inside this volume, points that are outside continue to remain outside, points that are on the surface continue to remain on the surface. Because if a point were to go from inside to outside, that means that it has to cross a point on the surface, and if it crosses a point on the surface, then the velocity is not single valued at that particular location. Okay, so, the requirement that the fluid velocity field is a single valued function means that points cannot cross the surface. What is inside continues to remain inside, what is outside continues to remain outside. So, for this differential volume, since material cannot cross the surface, the mass conservation condition is simply that the total mass within this differential volume has to remain unchanged in time. It should be independent of time. So, the mass within this volume should be independent of time. That is, dV times rho is the mass within the volume. Rate of change of that mass has to be equal to 0. Okay. This we transformed using the Leibnitz rule, if you recall, by accounting for the fact that as this volume is moving, certain regions are coming in because the volume is sweeping them in as it moves, and certain regions are being left behind. And if you take these two into account, this can be transformed into partial rho by partial t plus integral of the surface of rho times u dot n is equal to 0, okay, where n is the outward unit normal to the surface locally. At every point you have an outward unit normal that is defined at the surface. That outward unit normal is n. This can be simplified using the divergence theorem to give integral dV partial rho by partial t plus divergence of rho u is equal to 0. Integral over a surface of some vector dotted with n is equal to integral over the entire volume of the divergence of that vector. In this case, that vector is the whole thing, the density times the velocity. Okay. And this has to be true at each and every point within the volume, which means that my mass conservation equation becomes partial rho by partial t plus del dot rho u is equal to 0. If I were using Cartesian coordinates, I would just write this simply as d rho by dt plus partial by partial x I of rho u I is equal to 0. Okay. However, if I were to use a spherical or a cylindrical coordinate system, I have a definition of divergence. Okay, I have a definition of divergence and we saw how to get that. So, we just substitute that definition of divergence here. Okay. momentum conservation, rate of change of momentum is equal to sum of applied forces. Okay. For this moving differential volume, what is inside continues to remain inside and what is outside continues to remain outside. So, the rate of change of momentum of that material element is equal to the sum of the forces that are exerted on that material element. The rate of change of momentum is d by dt integral over the volume. The volume itself is a function of time, rho times ui. The density times the mean velocity integrated over the volume gives me the momentum. D by dt of that is the rate of change of momentum. That is equal to the sum of forces acting on this volume, two kinds of forces, body forces and surface forces. Okay. Body forces are proportional to the total volume, okay. Integral dv rho times ai, where a is the acceleration vector, okay, and rho is the density, okay, plus surface forces over the surface, okay, where r is a surface force. Okay. Examples of body forces, gravitational forces, centrifugal forces, all of these are proportional to the total volume. Okay. So, if the total mass is equal to the total mass within the volume is equal to rho times dv times the acceleration. The acceleration vector is the gravitational acceleration vector for gravitational forces, omega square by r in terms of omega square r in the case of centrifugal forces and so on. So, these are all proportional to the total volume of the fluid. So, I call volumetric forces. The other types of forces are surface forces. These forces exerted at the surface by the fluid outside on the fluid inside. Okay. These correspond to the momentum diffusion process, okay, the transport of momentum due to diffusion. These are the surface forces. Okay. And obviously, just as in the case of mass and heat diffusion, the fluxes are related to the gradients in the concentration temperature field. In this case, this momentum flux across the surface, okay, momentum transferred per unit area per unit time, will be related ultimately to the gradients in the velocity of the momentum fields. Okay. Now, you can do the Leibnitz rule for the left hand side as usual, okay, and what you get is that integral dv partial by partial t of rho ui plus integral ds, okay, of u dot n times rho u. Okay. I have already used index I for the vector momentum. Note that this is a vector momentum equation, contains 3 components. So, I get the vector momentum times u dot n, uj and j is equal to integral dv of rho ai plus integral ds of the surface force. Okay. So, that is the total momentum conservation equation. For the second term on the left, you can use the divergence theorem once again to get integral dv partial by partial t of rho ui plus integral dv of d by dx j. Note that the unit vector n had index j. Okay. So, the divergence has to be with respect to that same index, okay, of rho ui uj is equal to integral dv rho ai plus integral over the surface of the surface force. Now, last class I had done the Cauchy's construction for you in order to show you how R I can be expressed in terms of a stress tensor and the local unit normal. Okay. Basically, R I is the force exerted, okay, if I expand out a small region over here, okay, if I expand out the small region over here, okay, R I is the force exerted by the fluid outside on the fluid inside. Okay, R I is the force exerted by the fluid outside or on the fluid inside. This could of course be in any direction. Okay, last class I had shown you it has tangential force, but it does not have to be so. Okay. Okay. The force exerted by the fluid outside on the fluid inside. Okay. Last class I had shown it as a tangential force, it does not necessarily have to be so. The force can be in any direction. Okay. The force exerted by the fluid outside on the fluid inside. Okay. Now, for the fluid inside, the outward unit normal is in this direction. It is going from the fluid inside to the fluid outside. Okay. So, the outward unit normal is outward. Okay. However, the force exerted by the fluid outside on the fluid inside has to be equal and opposite to the force exerted by the fluid inside on the fluid outside. Okay. Newton's third law. Okay. So, there have to be equal and opposite forces exerted on both fluids acting at the surface. Okay. So, therefore, this fluid inside has to exert an equal and opposite force on the fluid outside. Okay. For the fluid outside, the unit normal is acting inwards. Okay. For the fluid outside, the unit normal is acting inwards. Okay. So, therefore, if I reverse the direction of the unit normal, the direction of the force at the surface reverses. Okay. What acts on the fluid inside is opposite of what acts on the fluid outside, and going from outside to inside is just reversing the unit normal. Okay. So, therefore, the surface force has to satisfy the relation, the surface force acting at a surface with unit normal n is equal to minus the force acting at a surface with unit normal, which is minus n. Okay. And this of course suggests that the force can be expressed as the stress tensor times a unit normal, because if the force can be expressed as the stress tensor times a unit normal, then reversing the direction of the force automatically reversing the direction of the unit normal automatically reverses the direction of the force acting at the surface. Okay. Note that there is a force per unit area, and Tij is a second order tensor called the stress tensor. Using Cauchy construction in the last class, I had shown you that this is actually an exact relationship. Okay. The reason is because in this equation, if you look at all of these terms, they are all volumetric terms. Okay. They are all proportional to the volume. In the limit as the volume goes to 0, these terms will be proportional to the volume or the length cubed. Okay. This last term here is proportional to the surface area. Okay. And the only way that you can maintain a balance is if this last term can also be converted into a volumetric term, okay, in the limit as the volume goes to 0. Okay. And if this last term can be converted into volumetric term, then all terms are proportional to volume, and therefore, you will get an equation that remains extensive as in the limit as the volume goes to 0. Okay. And it can be converted into volume only if I have an equation of this form, because I have something dotted with n over a surface is equal to the divergence of that thing integrated over the volume. Okay. So, that is the rationale for this kind of a stress tensor. Okay. So, with this kind of a stress tensor, the equation that I get, integral dv partial of rho ui by partial t plus partial by partial xj of rho ui uj okay, plus the surface term integral dv ds ds dij and j, and this last term here I can also write it as a surface integral as dv partial by partial xj of dij. Okay, so, I write that as a volume integral, and once I have that, then all terms are proportional to the volume. This equality has to be satisfied for any differential volume that you take. Therefore, it has to be satisfied at each and every point within the fluid. Okay, so, that is the idea. Okay. So, obviously, if the equality is satisfied at each and every point within the fluid, my momentum conservation equation becomes partial by partial t of rho ui plus d by dx j of rho ui uj is equal to rho ai plus partial by partial xj of tij. Tij is now the stress tensor force per unit area in the I direction acting at a surface whose unit normal is in the j direction. Okay. Go back to the definition. Okay. The force direction is I. Okay. In this expression, the force direction is I. So, the first index I gives me the force direction. The second index gives me the direction of the unit normal here, j. Okay. So, Tij is the force per unit area in the I direction acting at a surface whose unit normal is in the j direction. Txx, force per unit area in the x direction acting at a surface whose unit normal is the x direction. Txy, force per unit area in the x direction acting at a surface whose unit normal is in the y direction. Outward unit normal, okay, important to keep in mind. Okay. There will be cases where you will see this written as minus Tij Nj. That is because in those textbooks they have defined the force with respect to the inward unit normal. Okay. Here we have used the outward unit normal. Okay. In cases where you see there is a negative sign in front of this last term here, that is because they have defined the force with respect to the inward unit normal. Since the divergence theorem is related to the outward unit normal, we will use this notation without loss of generality. Okay. If it is defined with respect to the inward unit normal, the stress term here will change sign, but also the constitutive relation, the equation for the stress in terms of the strain rate, there will be one sign changed there as well in such a way that the final equations remain unchanged. Okay. I had also shown you that this can be written by combining this with the mass conservation equation. This can be written as rho times partial ui by partial t plus uj partial ui by partial xj is equal to rho ai plus d by dxj of tij. So, that was my momentum conservation equation. Okay. Next, we had gone through and almost finished the angular momentum conservation equation. I will go through that once again, because if you are seeing it for the first time, it is a little difficult to understand, but it gives us an important lesson about the nature of the stress tensor. So, that is why I will go through that in some detail. The angular momentum with respect to any origin. Okay. In this case, we can take the origin of the coordinate system without loss of generality, but the angular momentum equation can be defined with respect to any origin. Okay. But that origin has to remain the same as this volume is moving around. Okay. So, the angular momentum I will define, it is a vector is equal to integral dv of x cross rho u, okay, where x is the displacement vector from the origin in this case. Okay. This is, I should write this as L vector. Okay. In indicial notation, I will write this as integral dv of epsilon I j k x j rho u k. And epsilon is the antisymmetric tensor, it is the same everywhere in space. So, it does not depend upon volume. So, in general I can take the epsilon out of this volume integral. Okay. So, I can write this as the angular momentum with index I is equal to epsilon I j k integral dv of x j rho u k. Applying the Leibnitz rule for this, rate of change of angular momentum within this differential volume is equal to the sum of the applied torques. Okay. That is the Leibnitz rule for this. I am sorry, that is the angular momentum conservation equation for this particular case. Okay. So, therefore, the angular momentum conservation equation statement is going to be d by dt integral dv epsilon I j k x j rho u k is equal to the sum of the torques acting on this volume. Torques are due to two kinds of forces. One is the volumetric forces, the body forces, the other is the surface forces. Okay. So, the body forces are of the form dv epsilon I j k x j rho times the acceleration, okay, plus a surface component, okay, which is equal to integral dv epsilon I j k x j times r k. R was the surface force. So, it is epsilon I r, so it is x cross r vector. Okay. X cross r vector can be written as epsilon I j k x j times r k. Okay. R itself is equal to t dot n. Okay. R itself is equal to t dot n, where t is the stress tensor. Okay. So, this I can write it as epsilon I j k x j t k l n l. Note that this, for this dot product r is equal to t dot n, I have to use a different index, because there are many indices that have already appeared 2 times and once. I have to use a separate index. In this case, it will be this index L, which appears 2 times to denote this dot product. Okay. So, this is equal to epsilon I j k x j t k l n l. Okay. So, that is the statement of the angular momentum conservation equation. As usual, we use Leibnitz rule to simplify this. Okay. So, I get integral dv epsilon I j k partial by partial t of x j rho u k plus integral the surface ds of epsilon I j k x j rho u k. Okay. Integral ds of this whole thing times u dot n. Okay. Partial by partial t of this whole thing, that is epsilon I j k x j rho u k plus ds of this whole thing times u dot n. So, for that other u dot n, I have to use a separate index now. Okay. So, I will use u, l and l. I have to use a separate index for that other u dot n. Okay. And this, the right hand side can also be simplified, epsilon I j k x j rho a k plus integral, I am sorry, this should be a surface, this should be a surface integral, and this surface integral also I have to convert into a volume integral. Okay. So, I convert that into a volume integral partial by partial x l. The divergence has the same index as the unit normal in the surface integral. Okay. The divergence has the same index as the unit normal in the surface integral. Okay. Times epsilon I j k x j t k l. So, that is the entire statement, okay, of this angular momentum conservation equation. Okay. So, we can simplify this. Epsilon is independent of time and space, x is independent of time. Okay. So, for the first term, I can simplify it as integral dv epsilon I j k x j partial by partial t of rho u k plus, okay. The second term is a divergence, okay, of, okay, convert the surface integral to a volume integral using the divergence theorem. In this case, the unit normal has index n, and therefore, my divergence also should have index n. So, I should get partial by partial x l of x j rho u k u l. Okay. So, this will end up being equal to integral dv epsilon I j k x j rho a k plus integral dv partial by partial x l, epsilon can be taken out, x j times t k l. Okay. So, that is the final statement. Okay. Now, in these two, I am going to use the chain rule for differentiation. Okay. In these two terms, okay, in these two terms, I will use the chain rule for differentiation to simplify the terms. Okay. In particular, I will expand the derivative into two parts, one of which is the derivative of this one, this x j here and this x j here. The second is the derivative of what is remaining. Okay. Okay. the second is the derivative of what remains. Okay. And all of these involve partial by partial XL of xj, okay, partial by partial XL of xj, that is equal to either 1 or 0. If j and L are equal, that is equal to 1, and if j and L are not equal, it is equal to 0. So, this is our familiar identity tensor delta j L. Partial xj by partial xl is 1 if j is equal to L, 0 if j is not equal to L. Therefore, it is equal to the identity tensor delta j L. Okay. Okay. So, let us expand and simplify. Okay. Integral dv epsilon I j k x j partial by partial t of rho u k plus integral dv. Okay. There should be an epsilon I j k here. So, let me just put that in. Okay, the antisymmetric tensor is in there. So, I have epsilon I j k into first is x j partial by partial x l of rho u k u l. Okay, that is the first term, plus the second term which contains the derivative of x l with respect to x j, that is just equal to delta j l. Okay. So, I get plus rho u k u l delta j l. Okay. On the right hand side, I have integral dv epsilon I j k x j rho a k plus integral dv. Once again, I do an differentiation using the chain rule in terms of those two terms x j and t k l. The first one will just be x j partial by partial x l of t k l plus t k l delta L j. Okay. Because partial by partial x l of x j is equal to delta L j times t k l. Okay. Now, this also has to be true for each and every differential volume. That means that this expression has to be satisfied at each point within the fluid. Okay. Since this also has to be true at each and every differential volume, this has to be satisfied at each and every point within the fluid. Okay. A brief simplification here. Okay. Delta j L times u k u L. Okay. It is non-zero only when j is equal to L. Therefore, delta j L times u k u L can be replaced by u k u j, okay, because delta j L is non-zero only when j is equal to L. So, in the expression, instead of u L, I can replace it by u j and remove the delta. Okay. So, I just replace u L by j and remove the delta function. Okay. Similarly, t k L times delta L j, replace L by j and remove the delta function. And I get t k j. Okay. Good. So, now this is true for each and every differential volume. That means that this has to be true at each and every point within the fluid. Okay. So, if I just write down since it is a volume integral which is true for every volume, that means that it is true at every point within the fluid. Therefore, the integrand itself has to be, if I remove the volume integral, the integrand itself in the equation has to be satisfied at each and every point within the fluid. Okay. So, collecting terms, first term is I will get epsilon I j k x j into partial by partial t of rho u k plus partial by partial x l of rho u k u l. Okay. That is these two first terms here, okay, this one and this one, and then I have this last term here. Okay. So, that becomes just plus epsilon I j k rho u k u j. Okay, that is the last term here. Okay. And on the right hand side, I have epsilon I j k x j rho a k plus epsilon I j k x j partial by partial x l of t k l plus epsilon I j k t kj after removing the volume integrals, and I should have an epsilon in this term as well. Okay, so, let me put that epsilon in. Plus T kj. Good. If you look at this term here, epsilon I j k is antisymmetric in the indices j and k. If I reverse j and k, I get the negative of the value that it originally was. U k times u j is symmetric, okay, because the 1 2 component, which is u 1 u 2, is the same as the 2 1 component, which is u 2 u 1. If I interchange j and k, I get exactly the same result. So, I have this double dot product of an antisymmetric tensor epsilon with a symmetric tensor rho u k u j. Okay. And as we had discussed earlier, the double dot product of a symmetric and antisymmetric tensor, that double dot product is equal to 0. Okay. So, this term now is equal to 0, okay, because it is the double dot product of an antisymmetric tensor, that is the antisymmetric tensor in j and k, and the symmetric tensor, which is u k times u j. Okay. If you look at all of these other terms, okay, all the other terms, okay, there are these 4 terms which are identical to the terms which were present in my momentum conservation equation. Okay. The first 4 terms are identical to what was present, if you recall, in this momentum conservation equation. I have epsilon I j k x j times rho u k partial t of rho u k plus partial by partial x j of rho u k u j plus rho a k plus the divergence of the stress. Okay. These 4 terms, okay, are equal to each other, the left hand side and the right hand sides are equal. Okay. So, which means that these 4 terms on the left and the right hand sides, okay, 1, 2, 3 and 4 have to be equal. Okay. The left and the right hand side with just these 4 terms has to be equal. What that means is that this last term here is identically equal to 0 if the momentum conservation equation is to be satisfied, because the momentum conservation equation that I just got you here is just equal to epsilon I j k x j times the mass conservation equation plus this additional term. The mass conservation equation itself adds up to 0. Therefore, this additional term also has to be equal to 0. Okay. So, I require that epsilon I j k t k j is equal to 0. Okay, for angular momentum to be conserved, and that has an important implication. Epsilon is an antisymmetric tensor, that double dotted with t has to be equal to 0. That means that t is a symmetric tensor, the stress tensor is a symmetric tensor in order to satisfy angular momentum conservation. Okay. That means that t I j is equal to t j I. Okay. It is a symmetric tensor. Okay. This is always true. T is always a symmetric tensor unless for some reason there are some microscopic torques that are acting on the system. Okay. In most general cases, in most fluids, there is no microscopic torque, and therefore, T will always be a symmetric tensor. There are some fluids which are for example, magnetorheological fluids, where under application of simultaneous electrical and magnetic fields, you may actually generate a microscopic torque, in which case it would not be a symmetric tensor, but those cases are rare. Okay. In most other cases where you do not have microscopic torques acting in the fluid, T will always be a symmetric tensor. The stress tensor is always symmetric. And that is the reason that in textbooks, when you see this differential volume being drawn, okay, and the force balance on this differential volume, it is usually drawn this way. Why is it drawn this way? Because this, in this manner, okay, the torque is actually symmetric. I am sorry, the stress is actually symmetric. Okay. Of course, the stress on top and below, okay, the stress on top here and the stress below here, okay, have to be in opposite directions, because when you change the direction of the unit normal, the direction of the force changes. Okay. However, I also have these additional torques over here. Okay, there is one here and there is one in the opposite direction here, and is drawn this way. Okay, as you can see, there is no rotational component here. Okay, in this particular case, okay, when T x y is equal to T y x, there is no rotational component. Okay. Let us discuss that in a little further detail. Okay. Let us take a differential volume, a coordinate system, okay, x and y. We usually take x 1 and x 2, but for simplicity in this case I will take x and y to make it to connect up to something that you are familiar with. Okay. Now, on the right surface, okay, the force per unit area in the y direction acting at a surface whose unit normal is in the x direction. The outward unit normal is in the x direction, okay, E x. Okay. That means that the force per unit area in the y direction is T x y. Okay. On the left hand side, the unit normal is in the minus E x direction. Okay. And of course, the stress, when you reverse the unit normal, the stress gets reversed, and so this becomes minus T x y. Okay. How about the top and bottom? Okay. At the top surface, the unit normal is in the plus E y direction. Okay, at the top surface, the unit normal is in the plus E y direction. The force per unit area acting at this surface in the x direction is the shear component of the stress. Okay. This is equal to T. I made a mistake here. The unit normal direction is x and the force direction is y. So, this should be T y x, and this is minus T y x. This is T x y, and this is the unit normal is in the minus E y direction, and this is once again minus T x y. Okay. And the symmetry of the rate of deformation tensor, that means that this T x y is equal to T y x. Okay. It is symmetric only if T x y is equal to T y x. Implication is that there is no net torque on this differential volume, because you can see that the forces on the top and bottom tend to rotate this in the clockwise direction, whereas the forces on the right and left tend to rotate this on the anti-clockwise direction. If the forces are equal, there will be no net torque on this differential volume. That is the important implication of the stress tensor being symmetric, and that is why typically in textbooks you will see the stresses, the shear stresses written in this fashion without any rotation. Okay. And that is because from angular momentum conservation, there is no net torque on the system, there is no microscopic torque on the system. The net torque on any differential volume has to be exactly balanced. Okay. Otherwise, you will violate angular momentum conservation. Okay. And this net torque is balanced if the stress tensor is symmetric. Okay. So, now let us look at the stress tensor. Okay. T, the second order stress tensor, T x x, T x y. Let's symmetric, therefore, these two are equal, these two are equal, and these two are equal. 6 independent components, okay, symmetric stress tensor. Okay. When we did the rate of deformation tensor, we said that the rate of deformation tensor can in general be expressed, any matrix can be decomposed into symmetric and antisymmetric. The symmetric further can be decomposed into an isotropic and a symmetric traceless tensor. The symmetric traceless tensor, the trace, that is the sum of the diagonals, is equal to 0. Okay. In this particular case, the stress tensor is already symmetric. Therefore, it can be decomposed into two parts. One is an isotropic tensor and the other is the symmetric traceless tensor. Okay. So, this I will write it as an isotropic tensor, which is T11 plus T22 plus T33 by 3 plus a second matrix, which I will call the symmetric traceless part. I will call it as tau, which will be the shear stress. Okay. So, two parts, one is the isotropic part and the other is the symmetric traceless part, tau. Okay. Physically, what do these mean? Okay. If I have a differential volume here, the isotropic part is the sum of the diagonal elements. T11 is the force per unit area in the x1 direction acting at a surface whose unit normal is in the x1 direction. T22 is the force per unit area in the x2 direction acting at a surface whose unit normal is in the x2 direction. Similarly, for T33. That means that these represents component of the force which acts in the same direction as the local unit normal. Okay. So, these are forces that are acting along the same direction as the unit normals. Okay. Front, back, up, down and left, right. Okay. On each of these faces, the forces are acting in the same direction as the unit normal. Okay. And tau is the component of the force which does not have, on average, there is no net force acting along the direction of the unit normals. Okay. If you add up the sum of the forces acting along the direction of the unit normals, in tau you will get basically 0. Okay. In our indicial notation, I can write this as Tij is equal to tau ij plus an isotropic part, okay, delta ij times 1 by 3 Tkk. Okay. Tkk repeated index, that means there is a summation, no unit vector. So, Tkk is T11 plus T22 plus T33. Okay. Therefore, 1/3 Tkk is what I have here, T11 plus T22 plus T33 divided by 3, that times the identity tensor is the isotropic part and the remaining is the symmetric traceless part. The symmetric traceless part has the property that its the trace, which is this, is equal to 0, okay, that the sum of the diagonals of the symmetric traceless part is equal to 0. Okay. What do these physically mean? If a fluid were just static, okay, if a fluid, there was no flow within the fluid, okay, just imagine a static volume of fluid. In this fluid, there is a force acting on the surfaces. Okay. On all surfaces, there is a force. That force is equal in all directions and it is called the pressure. Okay. So, at a static head of fluid, and if I go somewhere within that fluid and I put in a small differential volume and I measure the forces acting on all surfaces of that differential volume, all those forces will be equal, they will be acting inwards and they will be equal to the local pressure times the surface area. Okay. As you know, the hydrostatic pressure is equal and acts equally in all directions. At each point, okay, if you have a surface to measure that hydrostatic pressure, the force always acts perpendicular to that surface. Okay. So, the pressure is defined as a force that acts inward at each location, okay. Whereas, we have defined our forces as acting outward. Okay. Therefore, this 1/3 Tkk is just equal to the negative of the pressure, because the pressure at each surface acts inward. We have defined the stress with respect to the outward unit normal. Okay. So, this just this 1/3 of Tkk in a static fluid is just equal to the pressure. Okay. With the negative sign, because the pressure is defined to be positive when it acts inward, whereas I define my stress tensor to be positive when it acts outward. Okay. So, this pressure is present even in a fluid which is not moving. Okay. It's a static component of that stress. Okay. When the fluid moves, okay, in general, if the fluid is not moving, okay, when the fluid is not moving, of course, one cannot get stresses that act tangential to surfaces, because it is only when there is fluid flow and there is momentum transport across the surface can I get forces that are tangential to surfaces. Okay. So, only when there is fluid flow will I get these shear stresses acting at surfaces. In the absence of fluid flow, I just have a normal pressure acting at each surface. That pressure always acts inwards. Okay. So, the second component that I had here is the component of the stress due to fluid flow. Okay. So, to reiterate, Tij, the stress tensor, can be written as minus P times delta Ij, where P is the pressure, isotropic part of the rate of deformation tensor, plus the second part tau Ij. Okay. This second part, of course, depends upon the rate deformation within the fluid. Okay. And therefore, a constitutive relation will relate this tau Ij to the gradients in the velocity field. Okay. The constitutive relation will relate this to the gradients in the velocity field. In a similar manner to the flux, mass flux being related to gradients in concentration field, heat flux being related to gradients in temperature field. Okay. Secondly, this tensor is already symmetric. Okay. This tensor is already symmetric. The stress tensor as well as the symmetric traceless part are still symmetric. Okay. So, there is no antisymmetric component. Okay. The rate of deformation tensor had three components: symmetric, antisymmetric, symmetric traceless, antisymmetric, and isotropic. Okay. So, partial ui by partial xj had three components, okay, which was aij plus eij plus 1/3 delta ij times the divergence of velocity. Okay. There are three components, and as you can see, each of these represented specific forms of deformation. Each of these transformed differently under rotation or translation of the coordinates. Okay. So, each of these represents a specific form of deformation. Antisymmetric part represents one particular form of deformation, that is the rotational deformation. As I said, in the rotational deformation, there is no change in the relative distances between material points. When you have a solid body rotation about an axis, there is no change in the distance between material points, and because of that there is no deformation. So, stresses cannot depend upon this antisymmetric part. Okay. The stress could in general depend upon the symmetric traceless and the isotropic part. Okay. It could in general depend upon the symmetric traceless and the isotropic part. This tensor tau ij, symmetric traceless. If we make the additional postulate, okay, additional postulate that the stress tensor is linear function of rate of deformation. Tensor. Okay. It is a linear function of the rate of deformation tensor. Okay. Then tau ij cannot depend upon antisymmetric part, it cannot depend upon the isotropic part, because the isotropic part is isotropic, whereas this tau ij has to be traceless. Okay. So, therefore, there is only one way that I can relate the stress to the rate of deformation tensor, if it is linear. Okay. That is, it is proportional to the tensor itself, not to its higher order products. Okay. There is Eij times I am sorry, I could create higher order products such as EIK times EKJ, for example. That would be nonlinear in the rate of deformation tensor. If I postulate that the stress has to be linear in the rate of deformation tensor, then the only way I can get that is for the symmetric traceless part, I will have tau ij is equal to some constant times Eij, okay, because both the left and the right hand side are symmetric traceless tensors. I cannot have it proportional to the isotropic part because the trace of that is non-zero. This coefficient is usually written as 2 times mu, okay, where mu is equal to coefficient of viscosity. This coefficient of viscosity recall relates the stress to the rate of deformation, and this is the equivalent of the Newton's law of viscosity. Of viscosity written in tensor form. Okay. You are usually used to writing this as, for example, tau xy is equal to mu times partial ux by partial y. Okay. If I have an x and y coordinate system, orthogonal coordinate system. This form of the constitutive relation is not frame invariant in the sense that if I rotate coordinate reference frames, this will change. This equation will change. It's specific to a particular coordinate system where the flow is only in the x direction, the velocity gradient is only in the y direction. Whereas this tensor relationship that I have here is coordinate frame invariant. Okay. It works in any coordinate system that you choose to use. Okay. So, this is the Newton's law, the constitutive relation for the stress tensor, relation between the momentum flux and the gradient in the velocity field. Okay. And I could also have, in addition, an isotropic contribution due to deformation. Okay. I could also have, in addition to the pressure, I could have an isotropic contribution to the stress tensor due to the isotropic deformation. Okay. And that is often written in terms of what is called a bulk viscosity. Okay. This additional term, apart from the fluid pressure here, okay, apart from the fluid pressure, an additional term which is related to the divergence of the velocity, that is plus a bulk viscosity times the divergence of the partial. Okay, this is an isotropic additional contribution due to deformation, okay, an additional contribution to the viscosity due to the bulk radial expansion or compression. Okay. So, these two constitute the constitutive relations, okay, for what is called a Newtonian fluid. Okay. There is the stress rate of deformation relationship, the stress, the isotropic, the symmetric traceless part of the stress is related to the symmetric traceless part of the rate of deformation tensor through the viscosity coefficient mu. Okay. And you could in general have an isotropic contribution to the stress due to radial expansion or compression. And this pressure term here, okay, this is the usual pressure term, okay, which in the case of normal fluids will be given by some kind of an equation of state. Okay. In normal fluids, this will be given by an equation of state. Okay. So, combining these, the mass and momentum conservation equations, partial rho by partial t plus partial by partial x j of rho u j is equal to 0, that is the mass conservation equation, and partial by is equal to rho a I plus partial by partial x j of the stress, which we had separated into 3 components, minus p delta I j, the pressure, the static pressure which is present even when there is no flow, okay, plus 2 mu times E I j, okay, plus in general a bulk viscosity component. Plus in general a bulk viscosity component. Okay. You can simplify this a little bit. This is just equal to rho a I minus partial p by partial x I plus partial by partial x j of 2 mu e I j plus partial by partial x I of mu b partial u k by partial x k. And the left hand side, as you will readily recognize, is just the substantial derivative of the velocity field. Okay. The left hand side is just rho times dui by dt. Okay. So, these are the conservation equations for a simple Newtonian fluid. Okay. One could of course have more complicated forms of the constitutive relation in the case of non-Newtonian fluids. Okay. In that case, the stress is not necessarily a linear function of the rate of deformation tensor. It could depend in some more complicated way on the rate of deformation tensor. However, no matter how the relations are framed, one has to ensure that they satisfy the frame invariance. Okay. That is, if you translate or rotate coordinate systems, the resulting relationship should not depend upon the specific choice of coordinate systems. Okay. Basically, the difference between the Newton's law that I have written for you in tensor form here, okay, and that I have written for you in tensor form here. Okay. So, this one and the one that you would simply write for a simple one dimensional flow. Okay. So, the way I have written the Newton's law in tensor form, it is frame invariant, okay. And similarly, it has to be frame invariant no matter how one formulates an equation for a non-Newtonian fluid. Okay. So, we will briefly see how to formulate equations for non-Newtonian fluids in the next lecture, and then we will progress to completely specify the equations of motion for a Newtonian fluid itself in the limit, in the incompressible limit, where the density is not changing with position. The rest of the lectures will be restricted only to the incompressible limit. The incompressible limit is valid in most cases where the flow is not very fast, where the velocity is small compared to the speed of sound. In most applications that we deal with, this condition is actually satisfied. The velocity is actually small compared to the speed of sound, okay. And therefore, we can always use an incompressible equation to describe the flow. So, we will briefly look at non-Newtonian constitutive relations in the next lecture, and then go on to defining our equations and defining what are the boundary conditions that we need to satisfy these equations. So, we will continue that in the next lecture. We will see you then.